All right, so I may go ahead. Today's going to be short because I discovered something interesting. I go to look at the e-text, and they've disconnected me. You know, this happens for the first week with Pearson. Oh, now I'm connected again. Oh, shoot. Well, I'll be short anyway. It just had a glitch there. I don't know what happened. That's weird. I don't know. So I know Pearson will purge their system after, is it 2 weeks or 1 week? So what they do is after all the 14 days are done, they purge it, and then it's fine. I've never had trouble with it, but I've heard that they do that because the students came in last semester, and if you don't get it within 14 days and you go back to get it, you may have to connect with them. In other words, you might get a code. Like if you go to the bookstore, I think this is what happened to him. He went to the bookstore, he bought his little card. He waited, and he waited and he waited, and then he put his number in. But what happened is they had already purged and did the roll, so he had to call them, and they gave him a new number, and he got in the course. So there's something about if you get your number and you wait too long, I don't know. It's all this technology kind of drives you crazy sometimes. But it worked out. It bothered him for a day, and he was fine. So, but you guys have more patience with that kind of stuff than I do. So, let's see if I can. Okay.
Lightsabers are finally a reality, and you can own one. This new military flashlight is basically a lightsaber that fits in your pocket. But be warned, this $600 flashlight is not a toy. It's so powerful that it can melt through anything. It can even start a fire, making it the perfect...
Okay. Okay. So we'll watch this video in a minute, but before I do, I'll, since we are streaming, I'll do, see if I can find that paint. I'll talk about one topic, and I got to go a little bit early because I got to go to Conway, but so we found out before that the shear stress was equal to this times du dt, dy. And this is such that the geometry here is this. So like if you have a velocity here at top, and then your fluid layer kind of goes like this, and say this is the ground, and say this, let's just say that this is a big piece of plywood that somebody is pulling over here with a force, and this is a bunch of fluid in here. As you pull it, the fluid is going to resist it. That fluid is going to that resist the shear stress, which will be in pounds per square inch or square feet, or pounds per square feet. Then you can multiply it times the area of the piece of plywood, which is 32, and you can get the force that's required. Now, given that that's the case, this is basically what is called Newtonian fluid. And I heard you guys talking a minute ago about traffic, and actually what's funny, I don't know where any one particular person wants to go. I mean, I don't even know where I want to go. And it's so the thing is you'll get, after a number of years, I don't know how much you got left, but you'll get a mechanical degree. And let's say you get a job opportunity that deals with civil. And if you look at it, you know, for a minute, you'll realize, you'll have to, if you really stare at the mechanical curriculum and the civil curriculum, you'll find a few basic, very specialized courses in civil that if you took those, I mean, I'm thinking maybe 4, you could go past the PE exam for a civil engineer. Those are things like reinforced concrete, soils, there's a traffic course, there's one other that I can't think of it right offhand. There's at least 4, there may be 5. One of the things about traffic flow is it's modeled kind of like fluids. And so I think, okay, this is an old, it's 20-year-old knowledge. I think before you took your traffic flow course in the civil, you had to have your fluids. I don't know what's happening now. But the key is, traffic and fluids kind of behave the same way. There's a thing called Newtonian. Newtonian is kind of like, okay, if you think about it, you got water, Mickey Mouse. So Mickey Mouse is water, you know, the H2O. Then you got air. And air is a whole bunch of different nitrogens and oxygens ramming into each other and all this, carbon dioxide breathing in and out, carbon monoxide, all this. But what there are is they're individual molecules. Water's the same thing. They're individual molecules. And the thing we were talking about last time, where the traffic is going down the street and people are bouncing back and forth, that fits that model. So if you think about it, you know, let's say like you got air. You heat the air up and the molecules are moving a little faster. And if you start pulling across the top, they are bouncing around, but they're bouncing around in each other's layer as they are pulling, and they'll create this viscosity. It turns out that in everything, though, at low temperatures, it's easy to find this theoretically, but as it gets higher temperatures, like 80 degrees Fahrenheit, you really just have to go measure it, and you have to measure it as a function of temperature. So, in the book, it'll show you those graphs. But what is non-Newtonian? Non-Newtonian is basically things that are not Newtonian, and how are those classified? And this is kind of gross, but there's no girls in the room. But if you get sick one day and you sneeze, and out flops something on the table, usually you say, oh, that is a solid or a fluid. You can turn it, stuck to the thing, it may go down, you can poke at it, you'll find it has a weird behavior. And what it is there's long chain polymers, and they're all tied together. Your synovial fluid in your I almost said knees, but it's also in your elbows and everywhere. Essentially you have, okay, this is a simplified model. So here's your bone, and your bone's not square. Then there's this pad on the bone that's kind of like a sponge, has holes all in it. And then you got another sponge over here, and then another bone over here. Okay, so stuck in this is these what's called synovial fluid, and there may be little long chain polymers in there. Think about it. If you take water, if you take a hard substance, two pieces of hard substance, you put water in between there, push this one down on it, it's going to shove all the water off. Now imagine you have something that's different. You have long chain polymers, essentially very slick rubber bands. Rubber bands that, it's hard to imagine, but you can imagine this. You take a rubber band, you pull like this, and the rubber's going to, but imagine if it was very slick, and you put them in here, and then you squish them down. So you got these long chain, and you try to make contact metal. Those rubber bands are going to stick in there and keep the metals apart. This is essentially what happens in here. The cartilage is such that it's porous that some of this synovial fluid is going into the cartilage, makes it really hard for this bone here to touch this bone here, because it can squish and the synovial fluid will push out a little bit, but it doesn't completely eliminate itself, so this bone doesn't hit this bone. Now, as you get older, and possibly because of genetic wear, stuff like that, you can wear this off, and then you can have synovial fluid only. And when you got that, you're probably looking at not knee replacement, or is there's something else you can do before you do knee replacement? I don't remember. So the other thing, and okay, this is very beneficial on an oil rig. So you have this substance, right? And it's like a goo. It's like that stuff you sneezed on the table, although even more long chain polymers. You can put it on the table, and essentially it'll just sit there like this. We'll look at the video in a minute. And over time it might move apart, but if it has long chain polymers, it moves apart a little bit and it stops. It has an elastic component and it has a fluids component. It's a big goo. So let's say you had lots of oil down here somewhere in the ground. You had this chamber and you just shove this goo down the chamber. It's essentially going to fill up this chamber until it pushes, as a solid elastic object, pushes the oil back up the pipe. Well, that is if you had the pipe on the outside. I mean, I don't remember whether they push it on the inside or push it on the outside. I can't remember. But anyway, you push that stuff down. Sometimes you can push it down with hot stuff and get it to come out too. So you have a lot of things like that. It has an interesting behavior. One of the coolest things that I think is this. Take a Newtonian fluid like water, stick something like this on the end of a drill so it spins. It's perfectly cylindrical. And what happens in water is it slings the water to the outside and you'll get this little profile. Reason being, it's slinging and it's basically the water's just going around and around. Take a non-Newtonian fluid and do exactly the same thing. And what you'll find is it does the exact opposite. The reason it does that is it has long chain polymers. Egg whites is a good example. Egg white, if you do this, now you can get air bubbles stuck in there using a mixer, but if you just do this and try not to get air bubbles in there, you'll see it just climbing up a little bit. The reason being is because you have a long chain polymer, right? But this part of the polymer is closer to the drill bit than this. So it starts pulling it around the drill bit and stretching the polymer. And as it stretches it, you'll find that there is a tension around in this direction. It's wrapping itself around that drill bit and climbing it. And it's a very weird thing. So believe it or not, this course stays only in this area. It does not work itself into non-Newtonian. If you're interested in that, there's a chemical engineering course somewhere. I took one at Texas A&M, but they've got some other places. But here's a cool video, and we'll watch this, and then we'll call it good. Did I already start it? Oh, there it is. This guy is funny. Then, if I got to go, it's 22 minutes. We should be able to watch it before my ride to Conway comes. The other thing is, do we have volume? No, this whole thing fell out and falling apart.
Rheology, in its broadest sense, is a study of the relationship between force and deformation in continuous media. In this film, we shall focus our attention on fluids. We have marked a portion of a flow field outside the viscous boundary layer.
This is the key.
Here, water...
I bet. Realtek audio. What the heck? Oh, wait. Okay.
behaves almost...
Oh, yeah. We got audio now. Okay, now I can't cut it down. Okay, what do I do now? Okay, this is funny.
like an inviscous fluid. In the model of the inviscous fluid, the basic assumption behind the stress deformation relation, whether the fluid is at equilibrium or in motion, is that there are no shear stresses, or equivalently, that the pressure is isotropic. This statement, when combined with the balance of momentum equation, leads to Euler's equation of motion. In this flow, glycerin shows evidence of shear stresses.
So that's the parabolic.
Water and glycerin are two of many fluids that behave in a manner called Newtonian.
So notice it's like the traffic. They're stuck at the wall.
With no relative motion, the Newtonian fluid has no shear stresses. The pressure is isotropic. In relative motion, however, the stresses are linear functions of the instantaneous velocity gradients. If we formulate this stress deformation relation for the Newtonian fluid so that it is independent of the observer and couple it with momentum equations, we obtain the Navier-Stokes equation. There are many situations, however, for which these models are quite inadequate. This is especially the case when you are dealing with materials containing large molecules. This ball, for example, bounces quite vigorously, like an elastic solid. Yet, it really is a fluid. We'll come back to it later. Here's a viscous material, which I can pour into this beaker. No, I think I'll use this beaker instead.
It has such elasticity, it can fold itself back in.
I can even cut it to length. This material is a solution of a high polymer. Some other materials that do not follow the simple Newtonian model are molten plastics, egg white, paint, and mayonnaise. Mayonnaise holds its shape if you let it alone, yet it spreads with ease. Here is a more controllable experiment illustrating the same phenomenon. There is no stopcock at the bottom, and this vessel is open to the atmosphere on top, and yet this clay suspension does not flow. I can put this simple piston here, place this small weight on it, still no flow. Now a larger weight. It flows, but very slowly. A much larger weight. The flow is fairly rapid. I take the weight off, the flow stops. In a state of equilibrium, this material can support a shearing stress up to a critical value called a yield value. Even with materials not having yield values, the Newtonian fluid cannot explain many flow phenomena. For many of these, a more general model, that of the memory fluid, does provide an explanation. For the memory fluid, the pressure is isotropic in the equilibrium state where no changes of either the stress or the deformation are taking place. In relative motion, however, in contrast to the Newtonian fluid, the history of the deformation is significant. Instead of a linear function, the memory fluid reveals nonlinearities. In fact, nonlinearity affects both the shear stresses and the normal stresses. So, for the memory fluid, the stress is a nonlinear function of the history of the deformation gradient. For this model too, flow problems are solved by expressing this assumption mathematically and using the momentum equations. First, we will look at experiments demonstrating that stress does depend on the history of the deformation. This material exhibits both viscous and elastic characteristics. Honey has a high viscosity, but no elasticity. Remember the fluid ball? It was like an elastic solid during the short impact of bouncing. An elastic solid has a preferred configuration to which it will return when stresses are removed. A viscoelastic fluid behaves similarly if the stress has been applied only for a short time. But in contrast to the elastic solid, the fluid's memory is not perfect. This time-lapse sequence shows that if the stress acts for a time long compared with the relaxation times of the fluid, the fluid forgets its previous state. In reality, it took 45 minutes for the force of gravity to change the ball into a puddle. This is a container of high polymer solution. I'll drop in a steel ball. Again.
Notice the rebound.
Once more in slow motion. This liquid too is viscoelastic. Here's some more polymer solution. I can put this cylinder into it. And turn it a full 360 degrees. When I let go quickly, it returns almost half the distance. This time, I'll hold it for a few seconds. Since the fluid has a fading memory, when I do let go, the recovery is a much smaller fraction of the original deformation. We can make quantitative measurements of viscoelastic behavior in this type of apparatus. The test liquid is confined in this annulus. The outer cylinder is held stationary, and we can apply a torque to the inner one with this weight, which we can hang there. A trigger here releases the mechanism. To remove the torque, there is a slip toggle there. We can record the response of the inner cylinder, that is, its angular rotation as a function of time, with the pen on a chart moving at constant speed.
They didn't have digital accuracy.
The weight of the recording pen is counterbalanced by this small weight. We have, of course, designed this experiment to minimize extraneous effects arising from the inertia of the fluid, the inertia of the moving parts, and from friction. The first experiment is with a Newtonian fluid designated by the letter N. A constant velocity is attained almost at once since inertial effects are small. Now the applied torque is 0 again, and the cylinder stops immediately. This time, the fluid in the annulus is viscoelastic. A constant velocity is not immediately obtained. Even though the stress is constant, the deformation and the rate of deformation are changing with time. Now the weight is disengaged. Let's watch that again. It takes a while for the viscoelastic fluid to acquire the steady state motion appropriate to the constant torque.
Comes out, it's exponential, it comes off. It's like a circuit.
When we remove the torque, we see the cylinder actually reverse its direction. Although no torque is being applied, the material is deforming because of the elastic character of the fluid. Not all the energy used to produce the flow was dissipated. Some was stored and then recovered. We have looked at some experiments showing that the stress depends on the history of the deformation. To illustrate nonlinear behavior, we shall do experiments in which the time-dependent characteristics of the fluids are negligible. Here we have two identical reservoirs with two identical outlet tubes. One contains a Newtonian fluid, the other a non-Newtonian. The levels are the same. At first, the non-Newtonian fluid flows faster. However, after a while, it is overtaken by the Newtonian fluid. The basic phenomenon occurring here is more easily seen if the pressure head remains practically constant. These are two identical burettes containing the same Newtonian fluid. The pressure head in one is twice that in the other. The ratio of rates of flow is also 2 to 1, as we expect from Poisson's law. But if we charge both burettes with the fluid exhibiting nonlinear behavior and apply the same ratio of pressure heads, the result is quite different. With this polymer solution, when the head is doubled, the rate of flow is more than doubled. It appears that the viscosity is less at the higher velocity gradient. This type of steady flow behavior is called pseudoplastic or shear thinning. There are some fluids that create a contrary situation. For this suspension, the viscosity is higher at the higher rates of flow. This is called dilatant or shear thickening behavior. In the steady laminar flow of incompressible Newtonian fluids through tubes, a single material constant, the coefficient of viscosity, governs the volume rate of flow and the velocity field. Here we get the familiar parabolic velocity profile. However, for more general fluids, the flow rate and the velocity field are governed by a viscosity function. For such a fluid, the velocity profile can be very different from parabolic. We have seen how nonlinearity affects shear stresses. It also has an unusual effect on the normal stresses. Here is some glycerin, and here is one of my wife's favorite recipes. Why does the cake batter climb the mixing shaft in contrast to the behavior of the Newtonian fluid? We can get a better idea of what happened there if we look at a simpler experimental configuration. This shaft is mounted to rotate inside the larger glass tube in a coaxial geometry. The shaft is a hollow tube with a hole through the wall. The force per unit area exerted by the fluid in the direction normal to this cylindrical surface will be indicated by the level of the fluid inside this manometer tube.
This is the rubber bands wrapping tightly around the tube and climbing.
The stress normal to the outer cylinder will be shown by the level of the fluid in this sidearm manometer tube attached over a hole in the outer cylinder. When the central shaft is rotated, a shear flow is established in the annulus. The polymer solution climbs up around the rotating center tube as the cake batter did. Because the fluid is so viscous, it took about an hour for the level of the fluid inside the tubes to indicate the steady-state stress difference. Note that the stress exerted by the fluid normal to the cylinder walls is greater on the inner cylinder than on the outer. This is in contrast to the behavior of a Newtonian fluid, where the centrifugal field alone governs the pressure distribution. Here is another apparatus where we can observe a related phenomenon. This time, the material is sheared between two parallel disks, one of which can rotate, while the other is stationary. The distribution of stress normal to the stationary disk will be shown by the level of the fluid in these glass tubes. Of course, this level will be uniform in the tubes if there is no rotation. Remember, this time we are not concerned with the flow in the annulus between the vertical walls, but with the shear flow in the narrow space between the flat plates. If the fluid is Newtonian, the height of the fluid in the tubes at steady state is a little less near the center than toward the outside. For a non-Newtonian fluid at the same speed, the force normal to the stationary plate may be considerably greater toward the center. Although the steady-state stress distribution between the plates is attained almost immediately, again it took several hours for the levels in the tubes to reach their final positions. Indeed, quite high stresses can occur near the center, and this principle has been used in the design of a pump for molten plastics. If the bottom disk is replaced by a very shallow cone, the stress normal to the stationary disk varies linearly with the logarithm of the distance from the axis of rotation. This logarithmic relation is expected for all memory fluids. These normal stress effects come directly from the nonlinearity in the stress deformation relation. This diagram represents steady, simple shearing between infinite parallel plates. In addition to the shear stresses, there are also normal stresses. For the Newtonian fluid, the normal stresses in these three directions are all the same. With nonlinearity in general, they will not be the same. We have just seen some experiments in cylindrical geometries. It is the inequality of the normal stresses on this infinitesimal volume element that gives rise to the normal stress phenomena which we have just observed. We have looked at some simple flow situations. Now let us look at two more complicated experiments. This tank contains two fluids, each of which is in its own compartment, but both of which can be subjected to the same air pressure. One of the fluids exhibits Newtonian behavior, the other non-Newtonian. The compartments have identical small orifices through which the liquids can be forced. Notice that with the non-Newtonian fluid, there is a considerable expansion of the stream as it emerges. When plastic articles are to be made by the extrusion process, the die must often be designed smaller than the dimensions desired in the finished product.
That's called die swell.
Here, a sphere is rotating in a high polymer solution. Dye, introduced at the left, reveals the flow spiraling inward at the equator and outward at the pole. For a Newtonian fluid, on the other hand, where centrifugal forces are dominant, we would look for flow inward at the poles and outward at the equator. We have illustrated some phenomena that can occur with non-Newtonian fluids. The degree to which they occur depends on the particular material and the particular flow situation. In any case, when dealing with new fluids, especially those containing high polymers and suspensions, one should be on the lookout for time-dependent and nonlinear characteristics.
So at least you should be aware if you get involved with anything that's polymer, that's the only thing I'd like you to walk away with, that it may not behave what you expect from this class. So my ride, I think, is outside. So So we'll talk about that a little bit more as time goes on.